All right, hello everyone. I'm Zachary Ashburn, and my ocean engineering project is called Redesigning Ocean Probe Launchers to Improve Reliability. Today I'm going to take you through what I've done over the past 2 semesters. My motivation for this project comes from firsthand experience. I worked for the Naval Oceanographic Office as an electronic technician, and while we are on survey, we regularly use the LM-2A expendable bathythermograph, or XBT, launcher to deploy XBT probes into the sea. They give real-time measurements of temperature over depth in the water column. This data is used to create sound speed profiles that are integrated into the sonar systems to improve their accuracy. The current design has contact pins inside the breech, which I will be referring to as the launcher head. Since they are somewhat exposed during operation cycles, they are susceptible to corrosion, pitting, and mechanical damage. This can result in poor connection, loss of data collection, and reduced effectiveness of the sonar systems. Because of its relevance to the survey, I believe improving the durability and reliability of this system is essential in order to maintain consistent and high-quality data collection. For clarity, I have this drawing of the XBT launcher. During operation, the breech, or the launcher head, is opened by turning the lever clockwise that's on top of it, and then that allows the head to swivel to the right, opening up the breech itself. Then an XBT probe canister is loaded into the breech adapter. The launcher is then pushed back into place, and the lever is turned counterclockwise, pushing contact pins into the top of the canister. After that, a pin is pulled from the canister and the probe falls through the launch tube and into the sea. The picture on the right shows someone operating the launcher head wrong and risking mechanical damage. She has her hand on the breech adapter, which really is going to do nothing for the breech itself. As she turns that handle, it's just going to allow the breech to fall freely. As I briefly mentioned before, the LM-2A XBT launcher is used to make sound velocity profiles. Accurate sound velocity profiles are essential for sonar performance and underwater target detection. Variations in seawater temperature change sound speed, causing acoustic wave refraction that affects sonar range, positioning accuracy, and tracking capability. XBT systems measure ocean temperature profiles to estimate sound velocity throughout the water column. During deployment, the XBT probe detects temperature data with its thermistor and transmits that data through thin copper wire spools contained inside the probe canister and the probe itself. Conductive contact plates on the top of the canister connect with the launcher contact pins to complete the electrical circuit. The system uses seawater as an electrical ground, creating a closed circuit between the launcher and the probe during deployment. Reliable electrical contact is critical for continuous data transmission throughout the probe descent. Loss of contact can result in incomplete or corrupted profiles, reducing the accuracy of sonar performance predictions and environmental assessments. So my problem statement for this project is that the current LM-2A contact pins experience mechanical and environmental degradation, leading to reduced reliability and increased maintenance. Honestly, sometimes it even leads to equipment downtime, which is a big problem while you're on survey. My objectives for this project are to improve the reliability of the XBT launcher contact system by altering the design of the contact pin system and how it is operated. I will then evaluate these alterations through testing. At the end, my main objective is to go back to work at the Naval Oceanographic Office and present these potential solutions to the problem, and hopefully make my job easier. My strategy for the technical approach had 3 main parts. The first was altering the geometry of the contact pin tips. In the picture on the lower right, you can see the original pin design. It's on the left side of that picture. It comes to a very fine and sharp point. This is seemingly to penetrate the contact plates inside the probe canister. My research showed that this is not always the best way to maintain electrical contact between 2 surfaces. So I came up with 3 different pin tip designs. The top is a rounded tip design that would increase the overall contact area with the contact plates. The second one below that comes to a fine point still, but has a more tapered angle. I thought this would help reduce any blunt force damage that might occur. The third pin tip features 3 rounded nubs to ensure points of contact are always maintained. The second strategy was making the pins out of a different metal. The current pins are made out of stainless steel, which are very strong but not great at conducting electricity. I did research into different metals and I found 3 different copper alloys that combine strength and better electrical conductivity than stainless steel. Those are beryllium copper, copper nickel, and phosphor bronze. My third strategy concerned modifying the launcher head or the breech adapter in an effort to force the user to operate the launcher responsibly. I came up with several designs, but the most effective and simplest turned out to be the design that you see on the bottom there. It involves drilling a hole into the breech adapter and threading it so that I can install a 5/8 plunger bolt from the bottom. This would prevent the launcher head from falling to the right until the user ensures the contact pins are fully retracted. Then they can retract the plunger with the attached ring. So design, this was actually the part of my project that took the longest. Once I settled on those ideas that I just discussed, I had to accurately model them so that I could effectively simulate their modification or fabrication. I used Fusion for all these tasks. I modeled all the contact pins, and then I switched to manufacturing operations. I spent many hours trying to make this rounded pin with CNC milling operations, but it never turned out right. It was always really warped. Once I switched to lathe CNC operations, it came out a lot better, and unfortunately we don't have a CNC lathe. For the breech adapter, after I modeled it, I was thankfully able to use CNC milling operations. I created an operation for drilling the hole with a 17/32 drill bit, the proper size drill tap for the 5/8 bolt selected, and then created a threading operation for the drilled hole with a 0.490 inch single form thread mill, which is the proper size for the 11 threads per inch rating of the selected bolt. The tricky and time consuming part of these simulations was getting all of the settings right. You have to consider spindle speed, feed speed, retract speed, different angle settings, etc. The metals I was dealing with were soft compared to stainless steel, so the speeds had to be just right to ensure a smooth finish while not damaging equipment or the metal rods themselves. For the sake of time and budget, I only moved forward with the rounded tip contact pin design. We don't have a CNC lathe here in the OE lab, like I said, so I reached out to the machinist at the Bachelor of Science department in Hattiesburg. After several conversations, he was able to make 3 beryllium copper pins, 2 phosphor bronze pins, and 1 copper nickel pin. Once I received them, I 3D printed these prototype sleeves that you see there on the bottom out of what it was, a PLA plus filament, so that had a little bit more strength. And then I installed them in the launcher head to ensure that they fit properly. The breech adapter was able to be modified here in the OE lab with the Tormac behind you. Thanks to help and training from Dr. Newtz, we were able to drill the necessary hole and get it properly threaded for bolt installation. And you can see in the top left there that the breech adapter was actually too big to fit into the jaw vise, so we had to cinch it down to the table there. And then on the far right, that's the copper nickel rod getting ready to be have lathe operations done to it. All right, so next came the mechanical testing. While I waited for the new contact pins to be fabricated, I installed the original pins back into the launcher head, which you can see in that picture on the bottom. With the plunger bolt in place, I performed 1,000 test cycles. This involved me turning the handle of the launcher head and letting it attempt to swing freely into the extended plunger of the bolt, which you can see in that picture there. The first one on the left, the handle is all the way up, and the plunger bolt stopped the launcher head from shifting to the side. And then I retracted the plunger, allowing the launcher head to move freely for XBT probe canister swapping, and then returned everything to the original position. Once I received the new contact pins, I installed them and performed 2 more rounds of 1,000 test cycles. To further test the metal used for the new contact pins, I built a salt fog chamber. This chamber is a sealable plastic container. Inside is a saltwater solution, an ultrasonic fogger, and a wire frame with plastic mesh to hold the specimens. Under the container are 2 silicon heating pads that are plugged into a temperature controller. The temperature controller uses a probe installed through the top of the container to detect temperature. I set the desired temperature to 100 degrees Fahrenheit, and the controller powers on the heating pads until the chamber reaches that temperature. While this is happening, the fogger is creating a saltwater fog that fills the heated chamber. I left the test samples in the chamber for 96 hours. Also, for the metal samples, I took 2 small sections of each of the 3 metal rods. One of the sets of 3 I left as they were. The other set of 3 I coated in gold using a gold electroplating kit, which you can see in that bottom left picture. This works basically by you have a heated gold solution, which is in that little white tub there, and you put the positive lead into it. The negative lead has a little alligator clamp, and you hold the metal sample with it and then dunk it into the solution. Once electricity is applied, the gold in the solution adheres to the surface of the metal sample. As we know, gold is a good conductor and is supposed to be corrosion resistant, so I wanted to see if this will have an effect while in the salt fog chamber. After the saltwater exposure, I would visually inspect the samples, weigh them, and apply a current to them. By applying a constant current and using a multimeter to watch for voltage spikes, I could discern if there was increased resistance and in turn assume damage from corrosion. By weighing the samples, I would be able to see if the corrosion caused any degradation of the metal, resulting in a loss of mass. And these are the results of the test cycles. On the left is the original contact pins, and then there's my 6 fabricated pins, and there was no visible damage detected. These are the results from the salt fog chamber. The samples showed minimal signs of corrosion. On that top picture, you have the beryllium copper, and then the copper nickel, and then the phosphor bronze. There wasn't a lot of corrosion, however, the gold did tarnish a good bit, and I had to scrape some of it off just so I could get the electrical current to go through it. Changes in weight were observed for all samples. Electrical continuity was maintained with all the samples, and although the plunger bolt does seem to be corroded a good bit, it's pretty much just surface corrosion, and the internal mechanism of the bolt was not affected, as you can see in that picture there. These are the aspects of my project that worked and what did not work so well. The geometry changes made to the contact pins did seem to have a positive effect on reducing stress to the pins and preventing damage. The new metal pieces showed good signs of resisting corrosion, and the test methods seemed to validate my concepts. However, while the electrical tests showed that the metals maintained electrical continuity, the voltage readings were somewhat erratic, and it was difficult to discern if the voltage spikes, if there were voltage spikes or just difficulties with the testing method itself. The weight readings were also a bit unreliable. Some metals showed a weight loss while some showed weight gain. This made it difficult to make reliable conclusions. The scale I used was in the chemistry lab and only measured to the milligram. I think a more accurate scale, hopefully down to the microgram, would heed more conclusive results. Also, to truly test stress on the contact pins, I would need a new XBT canister for every test cycle, but I only had the one, so it would be hard to justify doing 3,000 test canisters and not actually using them. This is my original budget. Miscellaneous hardware included things like drill bits, which ended up being more expensive than I thought, and the gold electroplating kit. For the machine shop fee, there was a bit of a miscommunication. I was under the impression it was a flat rate of $75, but the invoice I received was for $450. Apparently, the $75 applies to each hour of labor, which was 4, a general machine shop fee, and then a fee for the time spent prepping in the software. So I actually had $600 plus a $300 stipend, so that still covers the cost. These are the major skills I developed during the project. The main skill was designing and simulating infusion, which was very painstaking and time consuming. I also learned a lot about researching different materials, methods of conducting tests, and analyzing failures. This whole process has helped me hone how I manage projects and communicate them effectively. Some things I did not expect to learn. First, CNC simulations are much more difficult than I expected them to be. I thought I would be able to just insert my designs, pick some tools, pick an operation, and let it ride, but that was definitely not the case. Also, with actual CNC operations, one little mistake can cause problems. I forgot to make one adjustment while training with Dr. Newts and ended up cutting into the vice jaws of the CNC, which you can see in that bottom picture there, the damage done. Another thing, pay attention to the specs of the items you order. My first silicon heating pad was only rated for 12 volts, but my temperature controller output 120 volts. This was not disastrous, but the pad did not work as desired and even ended up melting the bottom of the container some. Finally, just as much time needs to be spent researching testing methods as time spent on concept and design, because that's where my biggest failure was. And on a personal note, I've learned that I really like 3D printing. I've been making all kinds of stuff this semester. Some things that could be done later on to improve the project. The new contact pins still require more rounds of testing, both mechanical and environmental. A key factor for pitting is the fluctuations in temperature, cracks getting bigger by expansions and contractions, so I'd like to introduce more tests like that. With the new pins installed in the launcher head, I would like to take the launcher back to the office and hook it up to our mock ship setup to make sure it passes the tests that we have there. I obviously need to come up with better methods of electrical testing and validating the effects of corrosion. Potentially like something in this top diagram, which is called a 4-wire Kelvin resistant measurement, might give better results. Also, the picture below it is a ORP monitor, which could read the corrosion potential of the water inside the salt fog chamber. Ultimately, I'd like to take the setup to the engineers at work and see if they want to try some real-world testing. In conclusion, I identified the problem with the design and operation of the LM-2A XBT launcher. During my project, I developed a variety of solutions and verified their impact through testing. In my opinion, this project is pretty close to being ready for testing on board our ships. This is our flagship here. It's the USNS Pathfinder, and I'll potentially be going there 2 or 3 weeks. Any questions?
What material did you ultimately choose?
I tested all of them, but I think the beryllium copper is the strongest candidate.
What safety precautions are you taking messing with beryllium copper?
Just when you're cutting it, you don't want to get all the dust. But every time you cut it, it's in a chamber. So.
And you're dealing with a solid piece. It's making an error.
Right.
Yes, you have to be careful when it corrodes. The oxidized point. It's highly toxic.
Yeah.
Okay. So when it oxidizes, it's going to be.
My main question wasn't necessarily that it's going to kill you, but it might get you in trouble.
Okay.
You know what I mean? Like you bring them on a ship, but you're bringing beryllium over here. It's not like bringing lithium on board. You have to sign for it.
Right. But we bring crazy stuff onto the ship all the time. As long as it's already installed inside of a piece of equipment, then they're not going to question it too much.
I mean, it's an alloy, right? There's probably very little beryllium.
It is an alloy, yeah. I don't remember.
So I don't know. Are you sure it's beryllium copper?
Beryllium copper, yeah.
Is highly toxic.
The biggest thing, so it's weldable. The biggest thing is when people are welding with it. Grinding or anything like that, it's going to make small particles. Welding is by far the worst. But like small particles like that. And it wasn't necessarily like he's dealing with a solid piece. It's already been machined. He's not dealing with anything. But like his point with the oxidates, like the dust that comes off it, or if you have to declare that you had it or anything like that.
Right. Yeah.
Because OSHA's starting to get a little bit insane about it.
That's true. Yeah.
Because you had, like a copper nickel alloy in there as well. Its conductivity not as good as beryllium copper, was probably almost as hard.
Yeah.
And if you said none of them really were damaged, kind of
They weren't damaged, but for fun, I took all of them out and then I smashed them with the breech adapter, and the copper nickel was the one that got the most screwed up.
really.
Yeah. I wanted to see some damage.
Which one held up against you smashing and against the breech deck?
The beryllium copper.
That one?
Yeah.
The top.
Yeah, it's really fun.
And honestly, the stainless steel did really well too, but
But
I
it
don't know what that.
Yeah.
Yeah.
So you had the old guns, the bolt that you pull out for the breech tester, and then you also have the new pins in the middle. Which you're gonna try and continue your research as to right?
No. Yeah.
Here now, no. Which do you think might get implemented first, if at all?
I think they would prefer maybe just the rounded tip design. Well, even the plunger bolt, because that's the main thing our engineers do there. They take existing equipment and they alter it for our needs on the ship. So the plunger bolt might be something they would actually want to do.
Easier, it's just you machine a hole and then
Yeah.
pull for it and it's done.
Yeah.
I mean, it's still functional with the same pins, right?
Yeah. And that's another thing too. I can go back because I modeled the original pins in Fusion. I really, hey, we can make our own pins now. We don't have to go through the lost pin.
I'm sure
It's all
like-
process.
And instead of getting new pins and having to order new pins, just having them drill a hole and the bolt would be cheaper, which is probably what they would do.
Yeah. But I was also trying to improve the electrical conductivity to the thing, because even when the original contact pins are good, sometimes we just randomly don't get good at sound velocity profiles.
Yep.
I mean, the plunger hole is also definitely your safest option because you know it won't do negative anything, right?
Yeah.
Well, the tips, maybe you learn year down the line, hey, all our measurements since we installed the new tips are no longer comparable, so there's quite a bit of risk.
Yeah, that's true. But they're open to having a test period for something, because we have there's another device that measures sound velocity. I can't remember what it's called right now. But we have it inside of the tank, and they had water run into it, and they decided for a year they were going to test more further up the pipe.
Mm-hmm.
So they're open to testing alterations.
Cool.
Oh, sorry.
Your presenting your results to the engineers there, is that like mechanical engineers in your department or like five?
Yeah. It's kind of a mix.
They're
There's a lot of
architects, isn't it,
mechanical
probably?
engineers, a lot of electrical engineers. But it's pretty informal. It's just like, hey man, what do you think of this idea?
Yeah. So this is like things like the process. Yeah.
No. I mean, not as far as I know. Anybody else? No. Cool.